The second video in this series on kinetic theory will be dealing with the states of matter. We're going to look at states of matter. States of matter, there are 5 states of matter. So in your notes, you have the major heading, Kinetic Theory of Matter. We just did the 4 assumptions of the kinetic theory. Now we're going to talk about states of matter. We're going to talk about states of matter and what qualifies something to be in whatever state it's in. And then I'm going to try to give you a metaphor that will make this really, really sensible in your head. So here we go. This is a cube. It is a cube. It has a definite shape that it is a cube. And what type of matter is this? You're very familiar with this. It is a solid. We are surrounded by solids all the time. We know what a solid is. The table is solid. The block is solid. The laptop is solid. The paper is solid. Even though it's flexible, it's still solid. What makes it a solid? Why is this a solid? How do you know that's a solid?
I don't know. You can hold it.
You can hold it. Yep. That actually plays into the actual definition.
It's like a liquid. It's hard.
It's not a liquid. Okay. It's not a gas.
It doesn't flow.
It doesn't flow. Okay. So these are all leading us to the very simple scientific definition of a solid is that it has a definite shape and a definite volume. That is to say, without changing the temperature or drastically operating on this with like a hammer or something, it is going to stay a cube. In fact, if I were to hold this out in my hand and it were a cube, and then it suddenly turned into a ballerina, you would be like, whoa, how did you do that? That would be like a magic trick, and you would think that that's not normal because you would not expect a solid to suddenly change shape, right? So we all know what solids are. We've just never really bothered to come up with the scientific definition. Scientific definition, definite shape, definite volume. Everybody got that?
Yeah.
You will not also be surprised by, you also will not be surprised by liquids because we are very familiar with liquids. Here's a liquid. It is in this flask. And what would you say about the liquid and its shape? Yeah.
It's got an indefinite shape.
It has an indefinite shape. It's going to take the shape of
Whatever you put it in.
whatever you put it in. So we like to say that a liquid will take the shape of the container. It will take the shape of the container, but only to the extent of the volume. So this is kind of like a half circle with the bottom cut off. If I pour it over here, the volume stays the same. It's about 75 milliliters. But now the shape is what? Cylinder. It goes from this funky sort of circular thing to cylinder. The volume of the liquid does not change, but if you pour it in the sink, it does. The shape will change. The shape of the cylinder will change. The shape of the liquid will change, but not the volume. Therefore, the scientific definition is definite volume, not definite shape. You are not unfamiliar with gases. This is a syringe, and if I open the syringe up, gas, air, goes into this volume here, into space. The gas, now once I close off the end, I've created a set space for the gas. If I change the shape or the volume of the space, the gas will change with it. So I can make the space smaller. The molecules of the gas, and now there's another concept we'll get to later, pressure builds up. Likewise, I can make the shape larger, and the gas changes to fill the space. Gas will fill the space of the container that it's in. This is Polo Club Fragrance Blue. It is Fragrance Blue. I am going to start here in the corner, and I'm going to spray on the table. Yeah, I know.
Ooh, that smells good.
She smells it already. It is propagated from the desk to her nose just that fast. You smell it? No, he doesn't like it. It's gone to the second desk. You smell it yet? Not yet? You smell it? It's in the middle of the room. I'm smelling it. You smell it? She has a sinus infection. You smell it? How about in the Jay? You not yet? It's coming. Don, you smell it?
Yeah, it smells good.
I want to smell it.
It's coming.
I want some of that.
A gas will expand until it fills the space that it's in. A gas will expand. It has no definite volume. Smell it? All right, Jay in the back of the room smells it. Gas will expand until it fills the container. Now he smells it. All right, it's getting there. Ah, I smell it really strong now. I just got like the wave hit me.
It smells delicious.
A gas will expand until it fills the space. And if it can escape the space, it will continue to expand. Now here's what happens. We're going to open the door and the cologne is going to go out in the hall. And the molecules are going to get farther and farther apart. And then they're going to go outside. And the container outside is called the atmosphere. So the container outside is the atmosphere. That little spray of cologne will eventually spread out until it fills the entire atmosphere of the planet. A gas will expand until the container is full. So if you put on perfume in Wisconsin, eventually perfume molecules will reach, assuming they don't react with something on the way or get struck by lightning, they will eventually reach Antarctica or Australia. Yes?
What happens once they pass the atmosphere?
But they can't. The atmosphere is a container. Gravity keeps them from going off into space. So now, the point about greenhouse gases is that if we create greenhouse gases in Wisconsin, those greenhouse gases will eventually fill the container that is the atmosphere. And so it is not like, well, we just have, somebody said in the last class, so the smog in New York reaches here. Yes, it does, in such small quantities that we really can't detect it, but it is not there. It is there, we just can't detect it. Our sense of smell, once that perfume, by the time the cologne reaches China, they won't smell it anymore because the molecules will be so far apart they can't have an effect on the olfactory senses. But that they will expand to fill the space. So that brings us back to liquid. Does not expand. This has got water in it. I cannot change the volume or the shape of the liquid. The volume or shape of the gas very easily changes. You can come play with these after we finish talking. Solid, definite shape, definite volume. Liquid, definite volume, not definite shape. Gas, not a definite shape, not a definite volume. Number 4, plasma. We're not probably familiar with plasma by this name. This is not blood plasma, but this is a state of matter. On every day that you come to school, you are surrounded by plasmas. The fluorescent tubes, the gas in there has a low pressure, and the electrons from the gas become the conductor for the phosphorescence in the tube. The sun is also a plasma. Lightning creates plasma trail from as it descends from the clouds to strike the earth. Plasma, here's the thing. It is such a high level of energy / low pressure that the atoms are moving so fast that they have thrown the electrons off. So let's say your golden retriever comes out of the pond and then he does that shake thing. He is moving so fast, he is vibrating in place so fast that he throws all the water droplets off, right? So that is how this plasma thing works. The molecules are vibrating so fast that they literally throw off the electrons. All right. Those are 4 of the 5 stages. Now I have a metaphor. Turn your imagination on. Imagination on. And envision not a classroom with desks and chairs, But envision a dance room with a dance floor and concessions around the room. We're now envisioning. And where, in this metaphor, we will talk about the tempo of the music, and it will be related to the temperature. So we have tempo, temperature. And now we're going to talk about the different phases of matter as different types of dancing. How about this? Told you, you've not done this in a class before. So we have the music, and the tempo is slow and subdued. And the couples, what do the couples do? They're made, and they might turn just a little bit. And so the couple, we would have like Mr. Sodium and Miss Chloride, who are clinging to one another as a couple. They are dancing together. And their movements are in harmony with each other. Even when they come closer and further apart from each other, but it's slow, and they really do not go anywhere. And now, in our dancing metaphor, there is a lady with a donut cart. Now, don't ask why. Just accept the fact that there is a donut cart, and there is a pool of people occupying the dance floor. And they are moving back and forth in place, but they are not making way for the donut cart. The donut cart cannot change the shape of the slow dancers. The shape of the slow dancers is fixed. The shape and the volume is fixed. Slow dancers are solids. The song comes to an end, and the tempo rises. The tempo speeds up to the next pace. The dancers begin a little bit more energetically engaging with each other. And one couple might move past another. And another couple might move past another. And they begin to maybe exchange place. And now, the donut cart lady can go across the dance floor. The shape of the dancers, now that they're going a little bit faster, the dancers have become liquid. And they will change shape. Even though they stay on the dance floor, the donut cart lady can pass through them because they're liquids. Crank it up a little bit more. It's getting pretty high. It's somewhere past shuffle, but not quite freestyle yet. We're past shuffling, but we're not freestyling. But the people are kind of spreading out. Now we've gotten to the gas stage. And the dance floor is no longer big enough because people are really moving around. So they're like backing off, and they're getting to the wall. And someone has moved over past the donut cart to the punch bowl area. And then where they have the cracker table, the cracker and cheese table. There are people there. If the room were bigger, the people would spread out. They're dancing so energetically that they're going to fill whatever space is available. And then it happens. We are moving from the gas stage to the plasma stage. The bow ties come off. The jackets come off. Those things called high heel shoes. One of them is in the punch bowl. The other one is lost and will never be seen again. Those corsages that came in on the wrist have been discarded into the corners of the room. The electrons are being shaken off the atoms. Who needs a bow tie when you're a plasma? Who needs a corsage when you're at the plasma stage? Who needs high heel shoes? Well, ever. But in the metaphor, the shoes go flying, the jackets go flying, the bow ties go flying. We have reached the plasma stage. No. It's just old 1980s dance, yeah. We have reached the plasma stage. One more. This one's boring. I cannot make a dance metaphor out of it. On the other side, everything goes down, 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 down. So I have my kinetic energy is 500. What if the temperature goes down? Kinetic energy goes down. So now it's 200. So now temperature goes down some more. Kinetic energy is 100. Temperature goes down some more. It's 20. Temperature goes down some more. Kinetic energy is 5. What's happening? I'm getting close to 0 kinetic energy. If the kinetic energy side of the equation is 0, then the velocity, because mass cannot go away, if kinetic energy becomes 0, velocity also becomes 0. That means that they're no longer wiggling. So there's this guy named Einstein. Anybody heard of him? Einstein? Einstein. Yeah, we've heard of him. And then this other guy named Bose-Einstein. Condensate. What does that even mean? What happens is, as the temperature goes down and down and down, the molecular motion comes to a stop. When the molecular motion comes to a stop, it has reached the Bose-Einstein condensate state. The state of matter called, or if you want to sound really intelligent, the BEC. What is the BEC? Well, the protons, electrons, and neutrons have clumped. That is a very fancy word for becoming a blob. Clumping or blobbing. The electrons, protons, and neutrons, no energy, 0, no motion. It's just a blob. You can read more about this on this website that I've referenced. What do you need to know? What do you need to know for the test? This italic stuff with the bold words. Blob should probably be in bold too. Clumping, blobbing, superatom, molecular energy nearly 0. Molecules are motionless. Motionless molecules, Bose-Einstein condensate. Kinetic energy nearly 0. Bose-Einstein condensate. Atoms clump together. Bose-Einstein condensate. Atoms become a big blob. You get the picture. Any questions about the states of matter? Yes?
What's even the matter with peanut butter?
Peanut butter is an amorphous solid, but we will get to that in a later chapter. Because if you heat peanut butter up, it will slowly become softer and softer, like butter or candle wax. It is an amorphous solid. So there we go. Guess what? We're done with the video. Thanks for watching. Hope you enjoyed it. Hit the like button. Subscribe to the channel. What was that channel you want me to shout out?
Oh, close my Instagram.
Instagram.
JaeBlank,
Add 2K setup.
Oh, whatever. So there it is. I'll put that down in the comments. Thanks for your help with the class, Jay. What else? See you in the next episode.